we can probably get started. So welcome everyone to the last seminar in the One World Combinatorics Onward seminar before we take a break for the summer. And we are very pleased to have Zachary Chase giving the talk today from the University of Oxford. And he is going to talk about three related problems: the separating words problem, the K-deck problem, and the trace reconstruction problem.
Okay. Can you hear me fine?
Yeah, absolutely.
Okay. Okay. Thanks a lot for the invitation. And yeah, so today I want to talk about three related problems that I really like. And for each of them, there's the gaps, there's an exponential gap between the upper and lower bound. So much more work needs to be done. So I hope this will entice some people to work on some of the problems. Okay, so yes, three difficult questions. So let X and Y be a pair of distinct 0, 1 strings of length n. Okay, the first question is there a deterministic finite automaton, a DFA with at most some constant times log n states that accepts X but not Y? X and Y are of course symmetric here, so it doesn't matter. The second question is there a string of length constant times n to the 1/3 that appears a different number of times as a subsequence in X compared to Y? And the third problem is if someone secretly chooses X or Y and gives us constant n² random subsequences of length n/2, can we say with high probability whether the secret string is X or Y? So like do a bunch of random subsequences of length n/2 look different from X compared to Y? Okay, so the outline of the talk is that we'll go through each of these three questions, explaining what is known about them, what is not known about them, and how they appear to relate to one another. So yeah, partial spoiler, there's much more work to be done. All three problems currently have an exponential gap between the best known bounds. So the separating words problem. So imagine a computing device with very limited powers. What is the simplest computational problem you could ask it to solve? It is not the addition of two numbers, nor sorting, nor string matching. It is telling two input strings apart. I think this is a quote by Jeffrey Chase. I saw it in one of his slides. Yeah, so for distinct X and Y, what is the smallest size of the DFA that accepts X but not Y? And the answer is just a function of n. In other words, we care about the worst case pair X, Y. Yeah, so just I think most of you know, but a DFA is just something like this. You have a bunch of states, a start state, accept states denoted with double circles, and then given a string, you just move from one state to another based on the bit of the string. So for example, if you input 0, 0, you start off at Q0, you go to Q1, and then you go to Q3, which is an accept state. So the DFA accepts 0, 0. And we say that the DFA separates two strings X and Y if it accepts one but not the other. So it's the above DFA separates 0, 0 and 1, 0. Okay, so yes. So the separating words problem was introduced in 1986 by Gralsic in Quebec. One could ask a similar question for strings of possibly different length, but this turns out to be relatively easy. So a trivial upper bound to this problem is n+1, which is, yeah. Okay, so the trivial upper bound is n+1, and in introducing the problem, they proved in their paper that you can have a sublinear number of states. So at most, like epsilon n for any fixed epsilon as n goes to infinity. They also showed a lower bound of log n up to constant. So there exists X and Y of length n such that no DFA with fewer than log n states can separate them. And the example they give is like one string is a bunch of zeros followed by a bunch of ones. The other one is a bunch of zeros followed by a bunch of ones. But the difference is that the two strings differ by either a block of zeros or a block of ones of a length that's divisible by all small numbers. So by like a periodicity argument, you can see that no DFA with fewer than log n states can separate them, because if you have a DFA and you keep putting in one, you'll get some period. Okay, And in 1989, Robson improved the upper bound. He showed that any distinct x and y can be separated by a DFA with O tilde n to the 2/5 states. The tilde here is just hiding logarithmic factors. So n to the 2, some constant times n to the 2/5 times log to 100 n. And we remarked that he begins his paper with a shorter proof of an O tilde n to the 1/2 upper bound. And we recently got a further improvement to the upper bound to n to the 1/3. And remember, the lower bound is still log n, so lots to be done. Oh, and by the way, anyone who wants to interrupt at any time, just say something. Okay, and then, okay, so I'll quickly go through the other two problems. And I don't want to like throw too much at everyone, but I'll say the two problems, what's known, and then we'll talk about the common approaches and how they come together. Okay, so for distinct, the KDEC problem is for distinct x and y of length n, what's the smallest length of a string w that appears a different number of times as a subsequence in x and y? So once again, the answer is just a function of n. We care about the worst case pair x and y. So here's an example. If w is 0, 1, x is 0, 1, 1, 0, y is 1, 0, 0, 1, then w appears twice as a subsequence in each of x and y. So like 0, 1 appears twice as a subsequence in x, and 0, 1 appears twice as a subsequence in y. Oh, I guess I should have clarified that by subsequence, I mean not necessarily contiguous substring, but yeah, okay. But 0, 1, 1 appears only once in x and 0 times in y. So the point is that, and you can check that for all strings of length at most 2, it appears the same number of times in x and y as a subsequence, which shows that for this x and y, like the smallest string that appears a different number of times has length 3. Okay, so the trivial upper bound to this problem is of course n, just because x is going to be a subsequence of itself but not y. The example on the previous slide is actually an instance of the 2 Morse word and its complement. Yeah, so that's an example of 2 Morse and its complement. And these pairs for n to the power of 2 and like sort of really close to it. They get bound up. And there were a couple of proofs of an n over 2 upper bound and some multiplicative constant improvements of the omega log n lower bound. Okay, so the known bounds were basically little c log n and big C times n for certain constants, little c and big C greater than 0. So okay, let's freeze introduce the notation f of wx for the number of times that a string w appears as a subsequence in a string x. So Scott in 1997, independently and concurrently, Krasikov and Rodady showed an upper bound of O tilde root n. So for any distinct x and y of length n, there exists a 0, 1 string w of length at most O tilde root n, such that f of wx does not equal f of wy. There was also a major improvement to the lower bound. So Dudek and Schulman in 2003 showed that there are distinct strings of length n, such that for all strings of length at most e to the square root log n, it appears the same number of times as a subsequence in x and y. And we briefly remark on their random construction. So for the 2 Morse sequence and its complement, those are generated by so-called like repeated substitutions. So more precisely, if xk and yk are the 2 Morse sequence and its complement of length 2 to the k, then xk plus 1 and yk plus 1 are formed respectively by concatenating xk and yk and xk. So in other words, to obtain xk plus 1 and yk plus 1 from xk and yk, we substitute into the pattern AB, BA, with A equals xk and B equals yk. So the Dudek-Schulman construction is by, excuse me, repeatedly substituting, sorry, if anyone has any questions. Sorry, is by repeatedly substituting the previous pair into a cleverly chosen random pattern that can and does change as the construction goes on. So instead of always plugging into A, B, and BA, you plug into more complicated patterns. Because of time, and I can't say everything about these three problems, I'll leave it there. Okay, so those bounds are still the best bounds to date, an upper bound of root n and a lower bound of e to the square root log n. I've tried for a while to get n to the 1/3 as an upper bound, but no success. I would really like to see an improvement. Maybe the lower bound is closer to the truth. Okay, so finally, we'll go over the trace reconstruction problem quickly. So take a string x and 0, 1 to the n, and define a trace of x. It's a random string. It's obtained by deleting each bit of x with probability half and concatenating the result. So here's an example of x in a random trace. So if x is 0, 0, 1, 0, 1, 1, 1, etc., the randomness is like, let's say it's such that the first bit is deleted, the second and third are kept, the fourth is deleted, the fifth is kept, sixth is deleted, etc. And then so the trace is just 0, 1, 1, 1, 0, 0, 1. So the trace reconstruction problem is as follows. There's an unknown string x of length n. And the question is, how many independently drawn traces of x do you need so that you can determine x with probability at least 0.9? So just to explain that you have this unknown string, here are like 5 independently generated traces. So this is behind the scenes in the sense that like you don't see what gets deleted. All you see is the concatenated result. So 1, 1, 0, 1, 0, 1, 1, etc. So you just see these things and you want to be able to guess this string with high probability. So to connect it to how I initially phrased the problem, you can view these as like random subsequences of length close to n over 2. It's not exactly n over 2, but it'll be close to that. Yeah, and we want the answer for kind of like worst case x, which isn't precise. Okay, okay, I'll skip over that. Okay, so going here, the first batch of bounds are an upper bound of e to the n and a lower bound of n. So the upper bound is trivial. You just wait until you see the whole string, right? Like if you have like e to the trillion n traces, like at some time you'll see the whole string. And then for the lower bound, it's harder to prove, but you consider the pair of all zeros except for a 1 in the middle, and you don't know exactly where it is. And intuitively, you'll need like a decent number of traces to figure out exactly where that 1 is, and it turns out to be n. And the main question here is whether polynomially many traces suffice. And the trace reconstruction problem is essentially equivalent to this pairwise version. So if we're correctly promised that the true string is either x or y, and we receive a bunch of traces from either x or y, we want to determine if the traces came from x or from y. And yeah, we want to answer as the function of n, so the worst case pair x and y. Okay, so the first bounds were n and e to the n. In 2008, Hohenstein, Mitzenmacher, Panigрафy, and Weider proved e to the square root of n. And this was improved in 2016 by Dao, Donnell, Servideo, and by Nazarov, Perez independently to e to the cube root of n. In 2018, yes, okay, so right now the gap is between n and e to the cube root of n. And in 2018, there was an improvement of lower bound to n to the 1.25. And then a year later, I improved this to n to the 1.5, just still far away from e to the cube root of n. And recently, I improved the upper bound to e to the 5th root of n. So these are still the best bounds. So the upper bound is e to the 5th root of n, and the lower bound is n to the 3/2. So once again, a lot of work to be done. Okay, sorry to throw those 3 different problems at you, but now we can talk about how they're related and go over like a common proof that gives bounds for each of them. Okay, so it turns out that the proofs of the n to the 1/2 bound for the separating words problem, the n to the 1/2 bound for the KDEC problem, and the e to the cube root of n bound for the trace reconstruction problem are all essentially the same, which I think is very interesting. And the proofs for the recent improvements of cube root of n and e to the 5th root of n bounds for the separating words and trace reconstruction problems are also essentially the same. Are there any questions? Okay. And more opaquely, one interesting thing is that for hard pairs for the separating words and trace reconstruction problems, you need to have like a common padding in the sense that like you can't have the two strings disagree early on. So if you want to like have something like the two more sentence complement be a hard pair for separating words and trace reconstruction, you're gonna have to take them and then like pad at the beginning and end by some common string so that they don't disagree too early on. For the separating words problem, if the two strings disagree early on, it's pretty easy to see that you can construct a DFA with few states that accepts one but not the other. For trace reconstruction, it's a little less clear, but I just find that interesting that for seemingly different reasons, they have this commonality of needing hard pairs to be padded at the beginning. Okay, so let's partially switch gears for a second and talk about the following number theory problem, and then we'll quickly relate it to the three problems we've been talking about. So here's a very natural number theory problem. So just quickly some notation for a subset A of 1 through n, a prime p and an integer I, just define AIP to be the things in A that are congruent to I mod p. So AIP is the stuff in A congruent to I mod p. So here's a problem. Given two distinct subsets of 1 through n, how small of a prime p can we find so that there's some I with the number of things in A that are I mod p is not equal to the number of things in B that are I mod p. So taking the negation, we're asking for the largest p so that there are two distinct subsets of n with the same number of evens, the same number of odds, the same number of things 0 mod 3, the same number of things 1 mod 3, the same number of things 2 mod 3, etc., all the way into the same number of things p minus 1 mod p. So I think this is a pretty natural question. Okay, and the answer is basically root n. So for any distinct subsets of 1 through n, there's some prime p of size at most constant square root of n log n and some integer I, so that size of AIP does not equal the size of BIP. In other words, the number of things in A that are I mod p is different than the number of things in B that are I mod p. And the proof is actually a very short and pretty proof. So suppose that this, I can quickly say it. So suppose that the proof is false. Then you look at the following polynomial. You sum from k equals 1 up to n, and the coefficient is 1 if k is in A but not B, and it's minus 1 if k is in B but not A, and it's 0 otherwise. So actually, this polynomial is actually easiest to view in the original setting. So if you have two strings x and y, this polynomial is like the sum of xk minus yk times e to the k. Okay, but this is obviously a polynomial of degree at most n, and under the assumption that the theorem is false, it has roots at z equals e to the 2 pi I m over p. For all p at most root n log n and all m. That's because when looking at this polynomial, when z is a pth root of unity, you can split the sum based on the residue of k mod p. So the point is that if this theorem is false, you can construct this polynomial with degree at most n and all of these roots. And that's a contradiction because the number of roots will be more than n. So the polynomial must be identically 0, which contradicts that a and b are distinct. So if you didn't follow the details, it's just this very like beautiful proof for this basic number theoretic problem. Okay, so there's also a more obnoxious proof of the n to the 1/2 bound for that problem that will be useful for later. So let's talk about it. So here's another problem. So you have two distinct subsets of 1 through n, and you want to find some non-negative integer m that's somewhat small such that a and b have different mth moments. So the question here is like, if you have two different subsets of 1 through n, what's the smallest moment that they can not equal? So they can have the same first, second, third moments, but can they have the same moments all the way up to root n? And the answer is no. And it's actually trivial to see that this implies the root n bound for the number theory problem, since if you look at the moment mod p, it splits into, it just splits based on the residues of a mod p for various little a and big A. Okay, and the point is that this problem is susceptible to complex analytic techniques. So it's easy to see it's equivalent to the following. So if you have any degree n polynomial with coefficients in -1, 0, 1, then you can't have too large of a power of x minus 1 dividing p of x. These are just equivalent. And the point is that intuitively, if x minus 1 to a large power did divide p of x, then p of x will be extremely small uniformly near x equals 1, which can be ruled out with complex analytic techniques. I guess I should have said p is not identically 0, but so the point is that this moment thing is equivalent to saying that you can't have too large of a power of x minus 1 dividing a polynomial with small coefficients. And if you did have that, then that polynomial will be like extremely small near x equals 1, and you can rule that out with complex analytic techniques. Okay, so here's the punchline. These three problems, the number theoretic one, this moments one, and the complex analytics one, all arise from and are basically equivalent to analyzing a type of single bit statistics for the given pair x comma y. So actually, it's okay. Let's go backwards here. So first, focus on the trace reconstruction. So for the trace reconstruction one, you look at the probability that a trace of x will have a 1 in position j. For the KDEC problem, you look at the counts of the number of subsequences of x of length k that have a 1 in position j. And for the separating words problem, you want to find a small prime p in some integer I, so that the number of ones in x that are at indices congruent to I mod p differs from that of y. So, okay, not focusing too much on the details. The point is that, like, for the trace reconstruction problem, we get a bunch of traces, and you just want to look at, you're just focusing on a certain index and looking at the probability that there's a 1 there. For the KDEC problem, you get a bunch of subsequences. You just want to look at the number of subsequences with a 1 in a certain place. For the separating words one, it's a bit different. Here you care kind of a modular version where you look at ones that are in positions congruent to I mod p. And the big picture point is that, like, these three problems quickly get you to the number theory problem, the moments problem, and the complex analytic one if you if you do have the computation. And for the separating words problem, like, you can construct a DFA on not too many states that does count like the number of ones and positions congruent to I mod p. Well, small technicalities, it gets that count modulo q for some q, but ignoring that for now. Okay, also, what's interesting is that if you run through the trace reconstruction argument of e to the cubed root of n with a very large deletion parameter, you actually recover the n to the 1/2 bound for the KDEC problem. So this is I say for concreteness because this is an example of how a concrete example of how the proofs are related. But if you care about the KDEC problem, then you can actually then you should actually care about the trace reconstruction problem, because you can view the KDEC problem as like the trace reconstruction problem with a very large deletion parameter. Because if you're looking at the multi-set of subsequences of length k can be like taking something there uniformly at random is equivalent in like a probability sense to taking a random trace where like the deletion probability is like 1 minus n to the minus 1/2. So the point is that if you have a very large deletion probability, the subsequence you end up with, that is the trace, will have length around n to the 1/2. So you're basically getting a random element from the multi-set of subsequences. Okay, are there any questions now? Okay. Okay, so given the above methods, it is natural to try looking at 2 indices instead of 1, right? So this was all about like looking at 1 index. You might want to look at 2. So for the separating words problem, you can look at the number of pairs of ones in x, the first at index I1 mod p, the second at index I2 mod p. And similarly for the KDEC and trace reconstruction, you can look at like ones at 2 different positions. And this idea probably does work and like probably does give an improvement in reality, but we currently don't know how to prove that it does. Yeah, okay, so that idea was looking at 2 indices that are potentially far away from one another. What if we look at contiguous indices? So it's easy to see that just looking at 2 contiguous indices won't be enough to get an improvement. So we have to look at many. So for example, for the separating words problem, we'd want to count the number of occurrences of a given string W of length around n to the 1/3 as a contiguous substring in X and beginning at an index that's current to I mod P. So here's an example. So let's say we want to count the number of times that a given string W, namely 0, 1, occurs as a substring in the string where it starts at positions congruent to 1 mod 2. So here's 0, 1 as a substring. It starts at 1, which is congruent to 1 mod 2. Here's 0, 1 as a contiguous substring, but it starts at 4, which is not 1 mod 2. And here's 0, 1, which starts at 7, which is 1 mod 2. So you get it appears twice as a contiguous substring starting in indices that are 1 mod 2. And it's still relatively cheap to build a DFA with few states that count such occurrences. And if we take the string W to be aperiodic, then the occurrences of W in a given string X are well separated from one another. Right? Like if the string W isn't like very periodic, it can't occur like very consecutively as a contiguous substring. So what this translates to is an extra assumption that we're given and can take advantage of in the number theoretic problem. So we say that a subset of 1 through n is D-separated if no two elements of it differ by less than D. So it's like any two distinct elements are separated by at least D. So the main technical theorem we proved to get the improvement on separating words problem to n to the 1/3 is the following. So you have two distinct subsets of 1 through n, and now you're also given that they're n to the 1/3 separated. So you want to show that there's some prime p of size at most n to the 1/3 and some I with the number of things in A that are I mod p differing from the number of things in B that are I mod p. So recall that without the n to the 1/3 separated assumption, the best we could do is n to the 1/2. So unlike the number theory problem I showed you before, where we don't have this n to the 1/3 separated assumption and we proved a bound of n to the 1/2, this statement has no like proof from the book. And you can actually make that kind of rigorous in the sense that there's like the previous proof gave a very strict cutoff. Like if you analyze the previous proof, you can see exactly the smallest prime that you can have. But for this, it seems that there's no cutoff, and it seems that you do need some log, like many logs in the O tilde. So I really doubt that there's a nice proof for this. So the way that we prove this is we take advantage of that more obnoxious proof from the previous number theory problem. Namely, we go up to the moments problem and then this polynomial near 1 problem. And the complex analytic techniques could indeed be adapted to give an improvement under the separated assumption. So we couldn't figure out how to use this separated assumption directly on the number theory problem, nor on the moments problem, but on the problem of a polynomial not being too small near 1, the separated assumption can be used to give an improvement. So unfortunately, it seems that no substring methods can help with the KDAC problem because you can have two strings with the same large KDAC, so of length, let's say log squared n, but they have a different number of occurrences of 0, 1 as a contiguous substring. So log squared n dec, that means the multi-set of subsequences of length log squared n. So the point is that for hard pairs, for the separating words problem, and for trace reconstruction, like the strings x and y will have the same substring occurrences, the same count of substring occurrences. But for the KDAC problem, you can easily see that that's not the case. And therefore, I speculate that substring methods won't be helpful. But yeah, as I've been saying, they can't help with trace reconstruction. So there are complicated formulae that recover good estimates for substring counts from few traces. I won't give the details, but that's true. Okay, so to summarize, for any distinct x and y in 0, 1 to n, there's a DFA on some number of states that accepts x but not y. The upper bound is n to the 1/3, lower bound is log n, so a big gap. The KDAC problem for any distinct x and y of length n, there's some string w of length at most something that appears a different number of times as subsequence in x and y. The upper bound is n to the 1/2, and the lower bound is e to the square root log n, so big gap also. And for the trace reconstruction problem, for any distinct x and y of length n, a certain number of random subsequences of length n over 2 suffice with high probability to distinguish between x and y. The upper bound is e to the 5th root of n, and the lower bound is n to the 3/2. So that's also a big gap. Okay, thank you for listening. That was very quick.
Oh, that's all right. It's lots of time for questions, I guess. So thanks very much. Does anyone have any questions for Zach?
For the number theory problem, is there a matching lower bound for your?
Are you talking about the first one, like with
Yeah.
no separated? Yeah. Pigeonhole gives the lower bound, maybe up to square root log factor. Yeah. So Robson actually has 2 papers on the separating words
Right.
problem. His second one actually gets the exact result where you look mod 2. So you look at like the number of things in A that are I mod P, and you look at this count modulo 2, and there he shows that constant root n is the exact answer.
Okay. Yeah. So your contribution is the matching upper bound then, yeah?
No, the matching upper bound was already known. The contribution was the new upper bound under the separating assumption. And there you also have a matching lower bound from Pigeonhole.
Yeah. So maybe perhaps my memory is just wrong. I thought in Robson's paper for the number theory problem, he only proved one direction, but
Which paper?
in one of his 2 papers, I thought that for the number theory problem, not for the automaton problem, I thought he only gave one direction of the bound, but maybe I'm wrong.
Okay. Either he did or in either case, I think it's trivial from Pigeonhole principle. So.
Okay. And the other question was, so you're doing pairs of things now, and I guess the obvious thing is triples, K tuples, and so forth, to try to get it.
Pairs, I don't know how to do pairs. The thing that ended up working was like contiguous substrings of long length. For pairs, you probably expect an improvement, but I don't even know how to prove that for pairs. But I think like if you do like pairs, triples, 4 tuples, I think you can get an n to the epsilon bound for separating words.
Yeah.
I just don't know how to prove that yet.
I see. Okay.
Yeah, I had a question. So is there some intuitive reason why it's so hard to close the gap between the upper and lower bound?
Yeah, so I had like thought about the trace reconstruction and KDEC problems for like a couple years before hearing of the separating words problem. And when I heard of the separating words problem, I thought like, okay, this has to be trivial. Like you're given like, instead of just having to look at like subsequences, you're given like the universe of DFAs. You can do whatever you want with the DFA to separate the 2. But yeah, I mean, I don't have a good answer. So it still surprises me to this day that the separating words problem is non-trivial, because like you have access to any DFA you want. Whereas like, for example, for the KDEC problem, the only thing you can use to distinguish is like the number of times something occurs as a subsequence. So yeah, it is very surprising that separating words is hard.
And which do you think is the true bound? Are the upper bounds the correct bounds, or are the lower bounds the correct bounds?
The lower bounds are all the correct bounds.
Okay.
For the separating words, that example might actually be I don't know if Jeffrey, you know this is false, but like that example I gave might actually be the hardest thing. But yeah. And
All right.
like, so there are, yeah, like, and to kind of see the upper bounds most likely aren't the truth, because you can look at pairs and triplets of indices and you get some math problems that are most likely true, but and you can use the computers to get some evidence for them, but they're just too hard to prove. So.
Right. Does anyone else have a question?